This is an Algebra 1 lesson on inverse variation. We've learned before about direct variation. Well, this is not that, and we will talk about that and how they're different. First thing we're going to do is talk about an area of a rectangle to give us an idea how this works. There's an exercise that's optional for this week. We'd be doing it in class if we were in class, but if you would do it first, it'd be great. It's the investigation right before 12.1. You get some points for it, and if you'll do it first and then come back and do this, it'll really help you understand it. First off, what are we going to have to do? Talk about the area of a rectangle. Okay, if we have a rectangle whose area is 24 square units, what could the dimensions be? Well, it could be a length of 1 and a width of 24. That would be 24. Okay, it could be a length of 2, width of 12, 3 and 8, 4 and 6. Well, wait, the length could be 6 and the width 4. That would work. And then down to 8 and 3, 12 and 2, and 24 and 1. Those are the whole number ones that will get us a rectangle with the area of 24. Notice as we're doing this that there's no 5 because 5 isn't a factor of it. But if you were to make a square, well, something times something's 24. Oh, wait, that's not a whole number, but notice that the square root of 24 times the square root of 24 is 24. So if you wanted this rectangle to be a square, and yes, a rectangle can be square, okay, it's still called a rectangle, then it could be 24 by 24, which of course you're not allowed to say. You're supposed to say 2 times the square root of 6, but we knew that, but we'll just talk about it for the moment because that's in the simplified radical form, or SURD. Okay, so what would these rectangles look like? They'd look kind of like this. There we go. So we'd have all of these have an area of 24. Here's the 1 by 4, 2 by 9, and here they are drawn out. And here's the possible square, whose side length is 2 times the square root of 6, or this, the square root of 24. So each one of these rectangles have an area of 24 square units. Notice I could make some that are in between, right? I could make 1.5 by 16. I could make 2.5 by 9 3/5, and then there's 1 in each between them, and there's, well, really, 1 between those, 1 in a 4th, 1 in an 8th, 1 in a 10th, 1 in a 100th. I could make rectangles that would make rectangles, but that have fractions or decimals that wouldn't be whole numbers. These are all the ones that make the whole numbers, and of course this one's not a whole number. So this is what they'd look like, the different rectangles that have the same area. Well, let's take a moment and graph that and see what it looks like when we graph it. I'm going to cover up part of it and then I'll come back to it. Okay. So if we just do the first quadrant, that's what we just saw. That's this. Okay. 1 to 24, 2 to 12, 3 to 8, 4. So this is, so what I've done here is I'm graphing it so that these are the coordinates of the point. Okay, what did I do to find the area? I multiplied by the length by the width. Well, if this is like the coordinates, then that's the same as multiplying the coordinates, miss. You're not supposed to multiply coordinates. Oh, today we get to multiply coordinates. It's kind of weird, but that's what we're doing. As we do this, this is what it would look like. 124, the length of 24, the width of length of 1, width of 24, or either way, whichever way you want to call it, whichever one you call an X and Y, it would come out this way. Does everybody see? Okay, look what happens. Remember how I mentioned that you can have the in-between ones like this square? You can have all the in-betweens, so it's a continuous function. We can draw it in. There will be values in between. Remember, continuous function means that there are values in between. That's like grass growing. Back when we were talking about continuous and discrete, we said that discrete was like how much it costs to go to the movie. And since it's times the number of people for the tickets, you wouldn't talk about having half of a person. So that one would be discrete. There wouldn't be values in between. But this one has values in between. We can draw a rectangle that doesn't have a whole number for its side, and it'll still make a rectangle. So then what is this the graph of? This is the graph of length times width equals 24. Or we can say in more general terms, xy equals 24. Does everybody see that, I hope? Not very good. That's not drawn very good. Now, a lot of times, especially if you want to put it in the graphing calculator, remember y has to be isolated. So we can divide both sides by x. So another way to write this would be y equals 24 over x. That's this graph. So in each case, it's just the length times the width is 24. If I write it this way, with y isolated, I do that because I want to stick it into the graphing calculator and see what it looks like. And by the way, if you put it in the graphing calculator, this will be what it looks like. Okay, well, back to this. Okay, that's the only way I can draw the rectangles. But what if I'm just talking numbers for a minute and I'm not talking an actual rectangle? Is there any other way I can multiply two numbers that are whole numbers, that are integers, and get 24? Yes, there is. Negative 1 times negative 24 is also a positive 24. So we could do each one of these with the negative. Okay. Before, when I didn't put the negative there, I talked about it being rectangles. Okay? Rectangles. Tell me, how would I draw a rectangle that was negative 3 by negative 8? Let me see. I want to try to draw a rectangle that's negative 3 by negative 8. Okay, well, there's a positive 3 and a 2 and a 1 and a 0. Wait, there's no negatives here. It must just be those imperial units. Surely the centimeters will have some because centimeters are cool and they use it in science. And well, it's 5, 4, 3, 2, 1, 0. Wait! There are no negative numbers. Why is that? Because a ruler is about measurement, and measurement can't be negative. A change in value or a change in place can be, but measurement can't be negative. So, I can't draw this. This is not a rectangle. It's negative, but nevertheless, it can still be quite useful, and I can plot it. And what it's going to look like is this. Okay? So, what we have here now is every one of them is negative. Notice it makes the same shape, but instead of being in the first quadrant when everything is positive, it's in the third quadrant where everything is negative. So instead of 3, 8, we have negative 3, negative 8. Instead of 12, 2, we have negative 12, negative 2. It's basically a mirror image across the line going down the middle. So, that's interesting. So this also then is x times y equals 24, or if you want to do it calculator language, y equals 24 over x. You still get it this way. Now, it's not a rectangle because you can't measure because there's no negatives. See, no negatives. All positives. Yes. Okay. So it's not a rectangle, but you can still do it, and you're still going to get the same curve. Okay, well, what if one of them were negative and the other positive? That's going to put it into the other two quadrants. So here, the x value is negative with the y positive. That means it's going to the negative to the left, and it's going up. it's in the quadrant that's to the left and up. And over here, if the x is positive and the y is negative, it'll be in the fourth quadrant. Okay, well, how would I write this? Okay, well, this one then is going to be, just a sec. Okay, this one is if one of them is negative. So what's that going to look like? So that means it's not going to multiply to 24 anymore. Well, here, what did I do? I said 12 times 2 is positive 24. Negative 2 times negative 12 is positive 24. Okay, 3 times 8 is positive 24. Negative 3 times negative 8 is positive 24. So if one of them's negative and one of them's positive, well, what do I do here? I say 3 times negative 8 sounds like negative 24 to me. Okay? And what is it? And so is that the case? Well, let's look. Okay, is that true of all of them? Because all of these, we've multiplied the coordinates, right? Weird thing to do, but that's what we did. And every time we got 24, look over here. Every time we multiply the coordinates of a particular point, and we get positive 24. Here, when we multiply the coordinates of these points, what we get is negative 24. The x value times the y value is negative 24. Or written in calculator is y equals negative 24 over x. Remember, we usually stick it out in front. Does that work over here? Negative 24 times, yeah, that's negative 24. Yeah, that's negative 24. 6 times negative 24. Yeah, that's negative 24. They're all negative 24. So over here, x times y equals negative 24, or in calculator friendly, y equals negative 24 over x. Notice that all of these are the same shape. They're just oriented a little bit differently. They make the same curve. One thing that's curious here, remember that really odd word that we talked about? Asymptote. We've done that before. Asymptote is the line that it does not cross. It gets close, but it doesn't cross. Well, let's look back at the real one that you can draw, the rectangle. Okay, what would happen if this is the length and this is the width? If we come down here and we say the length is 0. And then the width is going to be extraordinarily huge. Well, you know what? That's kind of silly because that just doesn't make a rectangle. So here's my width of my rectangle, and here's my length. There's no length. Okay? It's like, here I got a width, and here's the other width. And what's the distance between them? 0. Okay, well, that doesn't make a rectangle. All it makes is a purple stick. Okay? Now, if I had some distance between them, if I had some width, I could make a rectangle. But I don't have any. If it's 0, then all it is a purple stick. You can't make a rectangle with a side length 0 because it just goes, and that's the end of it. Okay? So, it's not going to ever actually get to 0. Like if the length was only, 1/1,000,000th of a unit, then it's going to be really long. When you multiply it by 24 to get it, it's going to be way high up there. And it's going to be a really long, really skinny rectangle. But you could draw it. But if the width was 0, So what we're seeing here is that it will never cross, in this case, the axis. Let me drop this on that there. Okay, it will never cross, in this case, the asymptote, or the straight line that will never cross, are the two axes. Now, in Algebra 1, most of the things are going to be the two axes as we had it before as the asymptotes, but that's not always the case. Okay. What do we call this thing? We call this thing a hyperbola. Okay. A hyperbola. A hyperbola. Not to be confused with a hyperbole. That's English class, and that's Miss Woodard. Or one of your other teachers. Miss Cher or Miss Parker. Yeah, hyperbola. So a hyperbola is this shape. And notice that the two blue ones get made with the same formula. There are two branches of a hyperbola. Okay? This is the same one. This is a different one, and it's two branches of the brown hyperbola. This is two branches of the blue hyperbola. Well, let's stop for a minute to think about how this works. Now, this stuff I'm about to tell you, you don't really need to know this, but sometimes it helps you know it. And if I was in the classroom, remember this little thing that's sitting on my desk? I would show you that and show it how it works. But you know what? I'm not in the classroom. So I've tried to make me one. Okay, let's think for a moment how you make a cone. Okay, mathematically, we talk about making a cone when we twirl around a line. Do you see what I'm doing? And see when I do it like this? Oh, let me see. Here we go. Can you see that I'm making a circle with the top of my green straw from Starbucks? Okay, there it goes. Okay, but also down here I'm making a circle. So when I twirl this straw, I'm drawing a circle like on the paper, and I'm drawing a circle in the air, and there's this one point in the middle that stays still. That's how you make a cone, and that's how you make the thing that we're going to get a hyperbola from. Since I don't have my handy dandy neat thing that's sitting on my desk, here is my cheap and dirty version of a cone. So what I would do here is, if I'm twirling this around, it'll form this. I twirl it around like this. It makes a circle up here and a circle down here, and it makes a cone. Mathematically, a cone is not just a snow cone with half of it. It's both of them together, because we think of a cone as the shape that a line traces when it twirls. Okay? Both top and bottom. So there are two parts of a hyperbola. Okay? And I've tried to draw here. If I had a thing in class, I could show you this, but I don't. This, see the line I've drawn on it? If I get it just right, it's pretty close to being a straight line, going from the one on the left to the one on the right with a space in the middle. See the line I've drawn? It's pretty close to straight. And that's what a hyperbola is. If you take a cone with two sections and you slice it, that's what you get. So if I take my cone and I make a nice cut, here's my bread knife, make a nice clean cut down here. I'm not going to actually cut it because that would make a really big mess. But imagine me cutting down here. Notice how on the curve, at the moment, that line that I've drawn, that black line, looks pretty straight. And I'm going to make this straight cut, and the cut I'm going to make is going to be parallel to the middle of the cone. So there's the middle of the cone. I need to hold it up so it looks right. Okay, there's the middle of the cone. And if I get it just right, that looks about parallel. I just drew it. Cut me some slack, okay? If I had my real thing, I'd show you. Okay, so I slice it off, and then I get a shape out of the cone that looks like what we just drew. One of the branches of the hyperbola. Okay? That light's shining kind of fine. And so you can see it. So here would be the hyperbola. But remember, I said you make a hyperbola or a cone by drawing a double circle, and there are two parts to it. So when I slice it, I would slice them both off, and that would be the shape that I would have. And that, sports fans, good friends, is our hyperbola. That's where it comes from slicing up a cone. You get one branch of it from the upper cone and one branch of it from the lower cone. And it comes from making a straight line, if I could get it oriented just right, chopping it off with my bread knife. Okay? So that's where it comes from, and that's why there's two of them. When you do a parabola, it's different. I didn't draw this one, but I can show you that if you ever come around, if we ever get to go back to school, which it doesn't seem like we're going to get to. Okay, so again, a hyperbola has two pieces. Two pieces to every hyperbola. We tend to forget the negative one, but they're both there. It comes from slicing up the cone with the bread knife. The ones opposite each other are the ones that have the same equation, and then the others have the negative. Remembering that in each case, it's multiplying the coordinates to get it. Now, a lot of kids have trouble with this because in some parts it's hard, but in some parts it's just like ridiculously simple. They can't say, is it really that easy? I just multiply them? And the answer is yes, it's really that easy. Okay. Yeah, it gets a little more complicated, of course. But that is the basic principle. So hyperbola is across. The asymptote, which was the word we've heard before, is the line that it gets very, very close to but does not cross. For a hyperbola, there will be two asymptotes, one for each of the coordinates. Remember the ones that we talked about before only had one asymptote, either on the horizontal or the vertical. Now also, they will not always be horizontal and vertical, but in this class they will be. Okay. So, what we have then is, I already did that. Okay, the standard form of the inverse function is right here. Okay, these are the ones that I just mentioned. Okay, so this is the way I always think about it. It's just like it's linked. You just multiply them and you always get the same number. Just like the ones we just did, we always got 24. Or if you did the book exercise, which I hope you did, you always get 12. You can write it in calculator-friendly form by isolating the y. And you can also think of this as the same as that. Now you can see that those are the same thing. It's just if you'd rather see it on its own. In this case, we call A the constant of variation. The way we say it is y varies inversely with x. Y varies inversely with x. So if you see that in a problem or in a situation, then you're going to say, aha, inverse variation. Remember, we had some problems before where we said y varies directly with x. That was direct variation, and it looked like this. Recall direct variation. That's just slope-intercept form with no intercept but 0. And recall that although this, some folks just like to say A, and then sometimes they want to say that it's a K for constant, even though constant starts with a C. It kind of sounds like it starts with a K. And then, but remember, it's the same thing as mathematically the slope. But it's going to be plus 0 instead of, the intercept is 0. Okay, so there's nothing out there. So direct variation, we knew that it always passed through the origin, and we could write a fraction about that. Okay, well, let's look at something to distinguish between them. Okay, first off, for direct variation, which one's which? Y equals 2x. Okay, well, if I have, let's just pick some numbers. If x is 1, y is 2. I put in a 1 for x, 1 times 2 is 2. Okay? If I put in 0, 2 times 0 is 0. What about if I put in a negative number? Negative 1. If x is negative 1, then y is going to be negative 2. What if I put in, negative 2? It's going to be negative 4. Okay, well, what do we have then? We have 1, 2, 0, 0, negative 1. Oh, it's looking a whole lot like a line to me. What do you think? It is a line. I'm really pretty sure it's a line. We'll draw it in there. It's a line whose slope is 1 and intercept is 0. Wait, the intercept is 0. This is direct variation. Okay. It's a line, and it passes through 0, 0. Remember, all of the points are proportional. You can make the same proportion when you do it. Okay, this is going to be 2 to 1, which is why the slope is 2. Okay. The next one. Direct or inverse? Y equals 2 times 1 over x. So what if I start with x is 2? 1 over x, that's 1 over 2. That's half of 2, which is 1. What if I say that x is 4? Okay, well then that would be 1 over 4 times 2. Well, that's 1/2. Okay. Okay, what about if negative 2 for x? Okay. Then that would be negative 2. That would be negative 1. Okay, well, let's look at this. Remember, inverse variation is you multiply the coordinates and you get the same thing. 2 times 1 is 2. 4 times 1/2 is 2. Negative 2 times negative 1 is 2. Okay, hey, that works. Well, I didn't put 0 in the middle. I should put a 0. So let's work that. 2 times 1 over 0. Uh-oh. That's the ultimate game over. You can't divide by 0. So this does not work, and the answer is not 0. It's just like, you can't do that, so quit trying. Okay, so what would this look like? This is going to be one that has 2, 1. Let's see, x is 2, y is 1. It's going to look about like this. Okay? And you can do the negatives, and they'll be along like this. And again, the axes will be the asymptotes. Okay? Yeah? All right? So this one is inverse. Okay, let's see what this one is. Okay, if I say x is 1, y is 3, 0, 2, negative 2, 0. Wait. Y equals mx plus b. That's a slope of 1 and an intercept of 2. A slope of 1 and an intercept of 2 is going to look like that. If I can draw the line. Okay, that's nothing. That's neither one of these. It is not direct and it is not inverse. Okay. All right. Let's look back for a minute at that square. Remember the square. Okay. So here's my graph, and here's my square. No, here's my square. I wonder what that square means on this graph. See, there's the square, and we noticed that the square root of 24 squared is 24. So if you want to draw a rectangle, and a square is a rectangle, that has sides that are the same, they're going to be 24 and 24. Okay, well, where is that on here? What's the square root of 24? You know, the square root of 25 is 5, so the square root of 24 is like almost 5. So let's look and see how that works out here, where almost 5 hits. So if I come in here, it should be almost 5 and almost 5. So there's 5, 5, so it's almost. So it's going to be about right in there at the square root of 24 and the square root of 24. That's what that point's going to be. Wait, the square root of 24, oh, look, x times y is 24, and if they're the same thing, multiplied by each other, then duh, yeah, that would be like x squared equals 24, and x equals the square root of 24. Yeah, that makes a lot of sense. Notice that this is the point that is closest to the origin. Well, what about over here? Well, that's going to be almost negative 5 and almost negative 5, right? So that's going to be like right here. And it's the closest point to the origin. Over here, it's going to be almost negative 5 and almost, oh, I said that wrong. This one's almost positive 5 and almost negative 5. Then this one is almost negative 5, almost negative 5. And this one is going to be almost negative 5 and almost 5. So in any case, they're all the closest part of the curve to the origin, or more generally to where the asymptotes intersect. Now in Algebra 1, it's going to be the origin. Algebra 2 and Calculus and later on, it'll be someplace different, and it'll still be the closest point to where they intersect. Okay? So the square root of our constant of variation is the coordinates of the point that are the closest to it. Now, when you get in Algebra 2 and Calculus, you'll have a lot more complicated thing to do. But for right now, in Algebra 1, this is working good. Okay? So if the length and the width are the same, then the coordinates of the square have to be the square root of 24. Length times width is the same, square root at 24. Right there, square root of 24 times the square root of 24 is the coordinates of that point. And this will be double minus and a minus and a plus and a minus and a plus. Plus and a minus, right? So that's how we know where the closest part is. It's the square root of the constant of variation, okay, on the hyperbola. So let's look here and let's see, is this a representation of inverse variation? Well, if that's the question, then all we have to do is multiply the x and multiply the y, see if you get the same thing. Well, let's try it. Negative 5 times 24. That's 12, believe it or not. Well, let's do the easy ones. Negative 3 times 4. That's negative 12. 4 times negative 3. That's negative 12. 8 times 1.5. Yeah, that's going to be negative 12. That one's pretty easy. Yeah, oh look, if you multiply them out and you tend to it, you're going to see that they're all negative 12. So yes, this is a representation of inverse variation. How can I write the equation for it? Okay, well think back. This is not hard. Okay, don't let it be hard. I multiplied the x and the y and I always got 12. I multiply the x and the y, negative 12, and I always get negative 12. Oh look, that's the equation. Calculator friendly form. It's negative 12 over x. Okay? That's what you do. Well, here, let's try a few of them. Make sure we can manage it. Okay, how about if x equals 5 and y equals 2 on a particular point? Okay? Okay, well, x equals 5 and y equals 2. What's the constant of variation? How do you get the constant of variation? And you just multiply them. What's 5 times 2? Must be 10. Okay? So x times y equals 10. If we want to write it in the standard form that the calculator likes, that'll be 10 over x. Okay? So what's the value when x is 1? What's the value of y? Oh, I put in 1 there, 10, that's 10. Does everybody see that? So some points here could be the 0.52, it could be the 0.110, it could be the 0.101. Does everybody see it? Okay? Because 10.1, if I put it in there, how did I get that? I just multiplied the x and the y. Okay? So what if we have x equals 3 and x equals 3 and y equals 7. Okay, so what's the constant of variation? You got it? Okay, you got it. 21, x times y equals 21 in calculator friendly form or standard form. There it is. Okay, you getting it? Okay, so what if we have a negative thrown in? What if x equals negative 5 and y equals 4? And I tell you it's and I tell you it's inverse variation. That's the key there. I'm telling you that I know that it is inverse variation. Write the form. You say, well, inverse variation, you just multiply them. Multiply them, you get negative 20. X times y equals negative 20. If you want it in the other form, negative 20 over x. I personally really like this one, but this one goes in the calculator, so it has its pluses. So hopefully you're getting the idea here. Now, you will practice, please. Please look on the website to find out to practice how to do it. Some of y'all are not practicing. You need to practice to do well before you take the quiz. There are also some extra assignments. So, here endeth the lesson.